you all for taking time and attending the seminar. So, so today I'll be going to present getting the best of both worlds, IoT and edge, using hierarchical inference. So before, okay, yeah. So before going to the presentation, I just want to quickly introduce what IMDAIA networks is. Maybe some of you might have heard. At least Motion, I see you. So Motion visited us last year. And I just explained what how IMDAIA network started to lead. So it was started back in 2007 when Europe wanted to accelerate research efforts and match the pace that at which US is going on. So they created specific, institutes for specific fields, and there are 7 IMDAIA networks in Spain. And the institute, IMDAIA networks here, it has like, we are 80 people, and among those 12 are faculty, we have now 13 postdocs, maybe it's a wrong number here, sorry, and then 40 PhD students. The research fields in which the faculty are working are mainly in network systems and algorithms, wireless networks, network measurements and analytics, distributed computing, and we also started like 2 years ago this quantum research work on quantum communications and networks. So I lead. Sorry, is there a question? Okay, I mean, if you have any questions, just please feel free to stop me and ask. And I lead Edge Networks group here. So we are a group of 4 people: myself, Andrea Fresa, Gina, and others. So I'm very fortunate to having working with them now. So with that, I want to go to the outline of this talk. So I'll quickly introduce about edge computing and edge intelligence. I'm sure most of you are heard about it or already working in it. And I want to talk about the key idea about hierarchical inference. This idea is for how to do deep learning inference or in general decision making at the network edge. And then I will try to demonstrate how hierarchical inference can be implemented for a straightforward application scenario, which is machine fault detection, and for a complex application scenario, which is image classification. So for image classification, we'll spend more time for this because, as I said, it's not trivial to do hierarchical inference for this application. So we'll go through a problem formulation, which happens to be a classical prediction advice, expert advice, with some challenges. Then we'll overcome that challenges and show some algorithms and the regret bounds we proved for them, and then present a performance comparison for different schemes using different data sets. So yeah, going back 15 years, so of course data centers were already set up, and then users or small enterprises are already borrowing or renting this virtual instances, and they are running their tasks. It was fantastic. It's going good. And then there was a huge surge in mobile devices, IoT sensors, even microcontroller units, all gathering information and sending all this information to some cloud, right? Now, what is the issue here? So why can't just data center support this? I mean, simply because of the latency issue. So once the first hop is the base station, and then there is the internet backbone, and then it has to go to the data center, and then collecting all this data into the data centers is also a challenge, because for some applications, like for in autonomous driving, these cars generate data at a rate that is an order of GBs per second, right? So simply the internet backbone cannot support this. I mean, we cannot scale the bandwidth to such levels. And there are other issues which are very important, but which I am not an expert in. So here, the data privacy issue, and you might have seen federated learning as one of the tools to alleviate this issue. Um, so data privacy and other concerns also come up if you want to do everything centrally in a cloud, right? So here it is, the edge computing architecture, where we want to not send everything to the cloud, but have some machines in between which has some computing capabilities. They are powerful enough to do processing that is close to the devices at the end of the network. So okay, good. Now we moved, like, since like maybe 10 years ago, since the inception of AlexNet, there was a lot of promising efforts in machine learning that started on. Okay. And then suddenly every application is using machine learning, right? So, or every complex application at least is using machine learning. So then it's natural thing. Sorry, is there a question? Okay. It's natural to have this edge computing architecture supporting machine learning applications, and we call this as edge intelligence, the confluence of edge computing and artificial intelligence. So you have different machine learning applications which needs to be supported on the edge server and also in the edge cloud continuum. Okay. So my work is in this context, and specifically I will focus on resource constrained. I will focus on the system here on the right. So we have resource constrained IoT sensors, or even they can be microcontroller units, or maybe mobile devices also. And they might be having some local algorithms, which can be machine learning algorithms, or some even classical machine learning algorithms like SVMs, logistic regressions. And at the edge server, there is a powerful machine learning algorithm, which can be a large deep neural network running. So in this setup, I want to focus on how we can efficiently do machine learning inference in this system in ML deployment phase. So I'm not talking about the training. I'm not talking about the federated learning or distributed machine learning setups. So this is on just the inference. Okay. So all these sensors, let's say they are embedded with pre-trained models, and now we are talking about this question: how to do this inference efficiently. Okay. Now let's look at the ways of doing the inference, right? So I can just collect all the data from these IoT sensors, okay, and then move it to the edge server and do remote inference. Okay, this has similar problems as we have seen in collecting data and doing something centrally, right? Like in the cloud. So what are those aspects? So first aspect is you require, of course, high bandwidth to collect all this data. And then if you're doing inference, the latency for transmitting the data and also doing inference on the edge server and getting back the result, okay, this will have comparatively large delay. And I'll come to large delay with respect to what, okay, I'll come to that. And this is less energy efficient, okay. By that I mean, if I can do inference locally on IoT sensors, which operate at milliwatts, on milliwatts power, I will gain in terms of, especially, again, there is a condition that if the inference is correct, then I'll gain in terms of energy, because if I want to do the remote inference for the same output, I have to transmit, which requires transmission energy, and energy at the edge server, which is consuming power in terms of watts. Okay, so I already hinted you, is the solution to overcome these challenges to just do local inference. Okay, but then if you want to do local inference, we already know these IoT sensors are resource constrained, right? So they have limited compute capability, low memory, limited battery life. If you look at a microcontroller unit, it will have a flash of 1 MB, and yeah, it just cannot do complex, I mean, cannot run complex algorithms, right? So because of that, if you are just sorting to low complex algorithms, okay, and if you look at the most successful application, the image classification kind of application, if you want to have any simple algorithm doing image classification, we cannot have high accuracy. I mean, now the state-of-the-art image classification deep neural networks are of order of GBs of 5, and they can go till 91%, 92% for ImageNet dataset, right? So so this is my point of interest, like how to do this distributed inference efficiently between IoT sensors and the large state-of-the-art DNNs running on the edge server, given these trade-offs. Okay. But there are, of course, some existing approaches which are already being implemented, right? So these things are already out there. So one is just do full offload. So considering, I mean, again, I'll come back to this image classification application. So if you want to just offload the images that are being maybe taken by an image sensor, you offload it, and then you get the inference back. That's the remote inference. And or you use tinyML. So there is this big machine learning community which is focusing on compressing the machine learning models to fit onto mobile devices. And there is this another community, tinyML community, which goes further, and they want to fit machine learning models, especially deep learning models, onto microcontroller units. So as I said, these microcontroller units have less than 1 MB flash memory, and their aim is to still get to a reasonable inference accuracy level, but should be able to have a deep learning model that is less than 1 MB. And then another approach for us to do this distributed machine learning inference is doing computational offloading. So in mobile edge computing and multi-access edge computing, computational offloading was a classical problem where you want to divide the set of jobs between the local device and the remote device. In this case, the jobs are simply doing the inference, right? So we just want to divide this set of images between local or remote, okay, and then perform the inference. The fourth technique is DNN partitioning. This is relatively new, I would say. Like after maybe in 2017, 2018, people looked at, yeah, why execute the entire DNN on a remote server? Okay, why not on less powerful mobile devices? By partitioning the layers of the DNN. So you do inference for first inference by sending the input on first few layers are done locally on a device, on a mobile device, and the rest of the layers on the on a powerful machine. So, and there is another technique which is also popular to do early exit technique. So the early exit is just in the deep neural network, you stop at a layer and check whether the inference at that layer is sufficient enough or accurate enough for you to accept or move on to the end of the deep neural network. So, but this technique, I would say, it complements, right? It can be used as part of any of the DNNs here. So there are also other approaches like doing collaborative inference, but so they have flavors of one or two of these approaches. Any questions so far? Okay. Then what we say is we propose a new deep learning inference at the edge technique called hierarchical inference. So in this, we mandate that the local devices should have some algorithm. It can be a tinyML model, or it can be any digital signal processing technique. Okay. And then we want to send this data sample through this local algorithm first. Okay. And then see the output of this local algorithm. So we call, if the local algorithm's inference is correct, we call that data sample to be a simple data sample. If the local inference on that data sample is not correct, we call that as a complex data sample. So then the idea of HI is quite natural. What we want is that the IoT sensors should accept local inference for simple data samples and offload complex data samples for remote inference. And at the first look of this definition, I mean, this is quite natural, right? I mean, this is what we want to do. So I would say this is not a definition. This is an intuitive thing, right? One should do. And then the reason I am defining simple data samples and complex data samples is that actually we'll see in many applications, there will be data samples which are easier to infer, and there will be data samples which are hard. Okay, this happens in many applications, and you'll have the larger number of data samples turned out to be simple data samples, especially in monitoring applications. But the key question is how to differentiate simple data samples from complex data samples, right? I mean, this is like a chicken and egg problem, right? We don't know actually what data samples have, I mean, the content of the data samples ahead of time, like which is easier to infer, which is not, right? So any questions here?
Excuse me, Jaya, what do you mean by data samples? Is it like
yeah, it can be
input
image
request to be inferred, or what?
Yes, it can. Yes. So yeah, exactly. Thanks, Motion, for asking.
And
so by data samples, I mean, we are having, we can have images, we can have, I mean, data examples, whatever data it is, right? The images or audio or time series, right? Any of
and then what do you mean simple and complex?
Yes. So we are saying that once you have a local algorithm that runs on this data sample and gives an inference, if the inference is correct, we call that as a simple data sample. If the inference is wrong, we call that as a complex data sample.
I see. Thank you.
Okay. And then for complex data samples, we want them to be forwarded or offloaded to the remote server so that a big machine learning algorithm, the deep neural networks, can give a correct inference, right? In the hope that it gives correct inference. Any other questions? Okay. So the question then is, as I said, how to differentiate this simple and complex data samples is one thing which I'll try to convince or advocate that it can be done to some extent. But then what are the challenges? Like, how is HI feasible? Okay. For HI to be feasible, the first requirement is that we need to have a local algorithm, okay, with the following properties. We should be able to have the size of this local algorithm that can be embedded, that is feasible to be embedded on an IoT sensor. And the computation energy taken by this local algorithm shouldn't be higher than the transmission energy, right, of this data, right, or the data sample. I mean, otherwise, why do I care? I mean, I just transmit. If the computation energy of the local algorithm is high, then I just transmit, right, and I get the best accuracy. But of course, I may not have the best, I mean, lower delay. But then the energy or the battery limitation of the device plays a key role, right? That's where we want to give more priority. So we need a local algorithm that is small enough, which can be embedded on IoT sensor, should have low computation energy, and it should provide correct inference for a large fraction of samples. That means we need to have large fraction of samples to be simple data samples, right, with respect to that local algorithm. Okay, these are the properties we need. And the second thing is, how can the IoT sensor know if the local inference provided by this algorithm is correct or not, right? So even if I design such a local algorithm, once it gives an output, the IoT sensor, if it has to decide to offload or not, it still doesn't know, right, whether this inference given by this algorithm is correct or not for that data sample. So in general, this is not possible, right? And there is no easy answer. How can we do this hierarchical inference, right? It depends heavily on applications, but I'll show its feasibility for machine fault detection and image classification application in this talk. Okay. So I'm just comparing with this existing approaches I have shown before, like we have full offload, tinyML, computational offloading, DNN partitioning. So in hierarchical inference, what we are doing is we are always sending this data sample through a small DNN that is local to the IoT sensor. Only when, I mean, the hope is only when it gives wrong inference, we offload it. Okay, so the advantages are, as I said, we are trying to utilize the full potential of the local algorithm, and also we are trying to not compromise on the accuracy, right? As I said, the local algorithms have relatively lower accuracy than the algorithms at or the deep neural networks at the edge server. And the good thing is we can actually implement HI. I mean, I'll talk about how we'll do that in image classification, but for local algorithm, for remote algorithms, so there are already, you can already get the machine learning models off the shelf, right? So there are tinyML algorithms, there are, of course, state-of-the-art algorithms, or you may try to do, you may try to jointly train the local ML and the remote ML algorithms to do hierarchical inference. But then there is no free lunch. Okay, the cost we pay is we have to use the local ML algorithm or local algorithm at least once on each data sample, right? To see what is, I mean, what is there, what is the content of this data sample at least. I mean, we need at least the inference, right? And any questions? So then we move on to these two use cases. Okay, so the first use case is the machine fault detection. Actually, it's straightforward to do HI here. So I will talk about what this rolling element bearings fault states are. So in rotating machines, there are these rolling element bearings, and these are the most common failures in these machines. This rolling element bearing on the right, if you see, there is outer lace, there is inner lace, and there is rolling element, the actual rolling element itself. And the faults might happen on any of these three layers. So the machine states are that this rolling element is working normally, or there is a fault on the rolling element itself, or there is a fault in inner lace or outer lace. So I'm trying to analyze a very widely used data set in machine fault detection community. So that is from the Case Western Reserve University. So they have this data set where they induce 3 types of faults on each of these layers. So based on the size of the fracture they make on each of these layers. So they induce this 0.18 mm, 0.36 and 0.54 mm size damages on these layers. In total, you have 9 fault conditions there, and you have 1 normal working condition of the REB. So you have in total 10 states in their data set. So you need to classify these 10 machine data sets, and the data they collect is the vibration data, and they collect at 48 kilohertz frequency. So I mean, the one of the latest state-of-the-art works, what they do is they collect all this. I mean, they propose to collect all these samples at a edge server, and then this time series data they convert into 64 by 64 images, and they send it to a convolutional neural network, so which is very good at classifying images, right? And it gives 99.91 classification accuracy for these 10 machine states. Okay. But if you look at this approach, if I just calculate bandwidth requirement just some handmade calculations. Say if I use 2 bytes per sample for transmission from the sensor, and then we are doing at 48 kilohertz frequency, so that itself will take 768 kbps just per second, just collecting the data from one rolling element bearing, right? And rotating machines usually have multiple of them, and the factory floor will have multiple rotating machines. And we can easily see if at least there are 10 machines, we can estimate that there will be at least 10 Mbps requirement easily. So the question I ask is, can the sensor transmit fewer samples without compromising the accuracy of detecting a faulty state? So any thoughts on this? So anyone?
Yeah, I think you're implying that you're going to use the hierarchy inference, right, to manage some of these things locally. And you
exactly.
You will only send the ones that the incorrect inference back, right?
Exactly. Yeah, that's where I'm going. I am trying to see if you can already find what we can do by not sending some samples. The hint here is typically a machine runs for hundreds of hours in normal state, right? So one thing I can simply say is I'll try to find, using a simple technique, I'll try to find when the machine is in normal working state. Okay. If I can find that and all faulty conditions, I exactly don't know which faulty condition I might encounter, but I don't, so for, I don't have to worry about. At least if I can know when this machine is in a normal working condition, I don't have to transmit too much data, except for time. I mean, like maybe some intermediate messages like time to live and things like that, right? So on the right in this picture, I'm showing you, so this time series data of the vibration data, I'm just averaging every 4,096 samples in a data set of 20,000 samples. And the for this 54 fault induced, and the 4 figures are for different horsepower. You can see that in cyan you have normal working states, and in magenta you have faulty states. Okay, you can already see that just doing averaging, okay, over 4,096 samples, there is already these states are separable, right? So if I use a simple thresholding algorithm, just offload only when the average is greater than 0.07 for this figure shown on the right, you can already separate the normal working state of the machine from other states. And I mean, indeed, here you can also separate the fault bearing state also. It can be also separable, right? Just looking from visual inspection. So what this already says is, if we differentiate this normal working condition from fault conditions by just doing averaging at the sensor itself, and only send when this average is greater than 0.07, you only send from there on to the edge server to differentiate the other faulty states, right? Because other faulty states, there are some overlap. So I mean, you can use the state of the art CNN to do that differentiation. So from this, we already have, I mean, this is actually a prototypical example, I would say, because so I'm just putting this in the context of HI, but in event-based control systems, this is already done. Okay. Any questions here? Okay. Now let's move on to the more interesting application, which is image classification. And this is joint work with Vishnu and James from KTH. So for image classification, we cannot...
Excuse me, sir. Yeah. I think you reduced the bandwidth, but you didn't tell us if your inference. Remember, you mentioned 99.91%.
Yes. Good question.
You still have the same accuracy?
Yes, because So whenever the machine is in normal working state, I am able to tell with 100% accuracy whether this is in normal working state or it's faulty state, but I don't know which faulty state. Okay. So when I know that there is a faulty state, then the sensor, right? When the sensor knows by doing just this averaging, right? When the threshold value goes beyond 0.07, from then on the sensor will transmit. Okay. And then the edge server has the state-of-the-art CNN. It will differentiate between these three faulty states.
Okay, thank you.
Okay, so now we'll focus on a more interesting application, right? I mean, of course, it's the bread and butter of many applications now. Here, of course, it's not as trivial, right? We cannot just have simple signal processing techniques, which cannot do good on image classification tasks. So we'll go back to the same requirements for if I want to do hierarchical inference for image classification. First, I need a local algorithm. Okay, first requirement is we need a low complexity DNN that can be embedded on an IoT sensor. Okay, but the tinyML rescues us. There is a lot of research now which has very good work done, like very small DNNs giving reasonable 70-80% accuracy. I think more than 80% accuracy for data sets like Cypher 10 and around 60% accuracy for ImageNet also. Okay, so for this work, I'll focus on mobile nets because in the experiments we use mobile nets, and I'll use mobile nets that's the smallest. So this mobile net is a deep neural network which can be scaled by using a hyperparameter alpha. So by that we mean you increase the width of the network and the depth of the network using this parameter. We use the smallest mobile net, where the hyperparameter value is alpha equals 0.25. And then you can see the model size of that mobile net is 0.5 MB. And its accuracy is pretty bad. It's 39% for ImageNet, the big data set. Okay. But then the state-of-the-art ML or deep neural network is COCA, which has more than 30 GB size, and it has 91% accuracy. Okay, that question is settled. So we have a local algorithm, mobile net. But the second requirement is the image sensor need to differentiate the correct inference from incorrect inference, right? So once you send an image through the mobile net that is embedded on the sensor, so the sensor has to decide now whether this mobile net give me a correct inference or incorrect inference. Okay. For this, what we'll do is we'll propose this hierarchical learning algorithm, okay, using which the sensor can learn whenever it is offloading some images to the edge server, it can learn whether its local, the mobile net, local ML algorithm, mobile net is actually how good it is, like it's giving correct inferences or wrong inferences. So that part we'll go in a bit elaborate detail. So, okay, that detail is here. So we need to first just understand how the mobile net output looks like. Okay, so once mobile net gives an output, so in the output, the softmax values actually they are a probability mass function, right? So each image class gets a probability value. So for example, if it's a binary classification for dog and cat, 80% dog, 20% is cat, right? And then this 80% is the higher value here, and then you try to classify that this image is a dog, right? And this value, 80% or 0.8, that value is the maximum probability among 0.8 and 0.2, right? So that value we denote in this work by P. Okay, let P denote the maximum probability value in this probability mass function you get. And as I said, we use that to classify the image, right? And the accuracy we compute is based on this P, the classes we classify using P. One can already get an idea that if P is large, the confidence of mobile net is high. Okay, And if P is small, then maybe it's better to offload this image because the mobile net is giving a wrong inference, right? So do you guys agree with this? So this intuition is, I mean, quite natural, right? So let's see for one particular data set, image net. Note that this is a subset of the big image net data set. I am showing here for each image, we are collecting this P value. So P is the maximum value among all these values in probability mass function that you get for each image. And I am looking at the incorrectly classified images and correctly classified images. So the correctly classified images are shown in color blue, and then the incorrect classified images are shown in brown. Okay. And then you can see that there is these are not mutually exclusive, in the sense there is an overlap, right? So you can see that of course for small p values we have large number of misclassifications. For large p value we have decently high number of correctly classified images, but there is also overlap, right? For even if you have large p value also, there is misclassification happening, and that's because that's the DNN is kind of a black box, so it is not clearly differentiating this, right? We don't have a clear differentiation, but then at least one can say that if my p value, okay, is so what is above 0.45, right? At this point, I don't know if you can see my cursor. Maybe I can just use, I don't know, here. Okay. In the interest of time, let me just continue. So if my p value is say above 0.45, I'm having images that are correctly classified are more than the images that are wrongly classified. Okay. And below 0.45, I have more number of images that are classified wrong compared to the images that are correctly classified. Okay. So can I say that, okay, whenever I get an inference, I look at this maximum value in this probability mass function, which is P, and I want to offload if the value is less than 0.45. Okay. Otherwise, I'll retain the inference. Okay. So now, do you agree that this is a sensible decision to make? Okay, if you don't have questions, then this is the key point we are trying to leverage on later. Okay, so then the question is how to choose this threshold, right? Because I don't know. Yep. Any question?
You're saying that 0.45 is the value of P that does the best differentiation between the simple and the complex images? Is that the point?
Yes. For this histogram we see, for this particular data set and for this local algorithm mobile net, this value 0.45 seems a reasonable threshold below which we offload. Of course, we are offloading correctly classified images also, right? Because if you see the thick brown ones are the intersection, right? So the thick brown ones below 0.5, the thick brown histogram are number of images that are correctly classified that you will be offloading if you just set this as a threshold, right? But that is still a sensible decision because above 0.5 we have less number of misclassified images that we are retaining, but reasonably high number of images that are correctly classified and we are retaining, we are not offloading. Okay, and that's the main, in hierarchical inference, this is what we want, right? The main objective is whichever the local algorithm is classifying correctly, we want to retain it. Whichever it is not, we want to offload it. Okay, that is how we are completely exploiting the potential of the local algorithm, right?
Sir, you put alpha equals 0.25. What is the alpha?
Yes, so in mobile net is a deep neural network which you can scale it. You can actually make it a bigger deep neural network by making more number of layers and the width of each layer by setting this alpha. Okay, so when I set alpha equals 0.25, I get the smallest mobile net. Okay, this is an image classification deep neural network.
Okay,
yeah.
Thank you.
Okay, so then I hope I convinced you that this decision is reasonable. And then the question we want to solve now is how to choose this threshold. We don't know this a priori. Of course, if I have all this information a priori, I know the threshold. But if the input distribution of these images is, I don't know a priori, I cannot know this P. And the rest of the talk, I will focus on how to choose such a threshold. Okay. So in order to do that, let me introduce the system model and the problem formulation. So I'm setting up the HI learning system model. We are sending each image through the mobile net first, and then we observe this P, and then the HI learning algorithm will make a decision whether to output that inference given by mobile net or whether to offload it. Okay. Once it offloads it, it gets inference back from the edge server. And if it doesn't offload but just gives output inference, there can be a local feedback, maybe some way you can get, for now say, some way you can get the local feedback saying whether this is the correct inference or wrong inference. Okay. So this is the system setup. So any questions here? Okay, so then HI learning algorithm, the decision it makes is if the P value it sees is below a threshold. So we'll get to see how this threshold is chosen. I mean, that's the learning part we'll see. Then it decides to offload. If the P value is below a threshold, then if the P value is above that threshold, then it accepts the inference of the mobile net. Okay. This is based on the previous slide, the explanation on the previous slide I was doing. Okay, and then the aim is to learn the best threshold that minimizes the number of simple images that we are offloading. Okay, whatever the images that got correctly classified, we want to retain them locally. Okay, don't offload. And then, as I said, we are assuming kind of local feedback here. Okay, once the mobile net gives the inference and HAL accepts the inference, the image sensor has no way to know whether that inference is correct or not. But maybe we can assume some scenarios where there is a human to tell whether this is a correct inference or not. So that scenario we call local full feedback scenario. And the scenario where you don't have a feedback at all, we call that as no local feedback scenario. And then we deal both of these scenarios. But for in the interest of time, I'll keep to the scenario where we have local feedback. Okay. So then here is the problem statement. So the images are coming in and we index them by T. And for image T, we have PT value. Okay, that is the maximum value in the probability mask function given for image T. And then for offloading, we consider beta is the cost. Okay, beta is, you may think, so here I'm doing an abstract formulation, but beta you can think of it as the offloading, the remote inference delay or energy consumption for offloading. Okay, and once the HAL accepts the inference, we have a cost YT. So YT will be 0 if the local inference is actually correct. Okay, or else we say the cost is 1. Okay, and then now you can see why we are choosing the offloading cost beta to be between 0 and 1, because if beta is above 1, then the decision is you always do local inference, right? Right, so that's the reason we are just choosing beta is between 0 and 1. Now, the decision for us when we are choosing a threshold theta, so theta t is our decision variable for threshold theta t. If pt is greater than theta t, we are accepting the inference, and then we get yt as the cost. If pt is less than theta t, we are offloading and we get a constant cost beta. Okay, and the total cost is summation of all these costs over small n number of images, say. Okay, and then the optimal threshold is what we want to decide, right? So which threshold we want to use, that is the argmin of the summation of this cost. Okay, so summation of L theta comma yt, and we want to minimize the total regret, which is the regret that our algorithm achieves, which is the total cost our algorithm achieves, and compared to the the total cost achieved by a fixed threshold policy. Okay, and then we want to find algorithms which have sublinear regret. Okay, so this is standard online learning setup we have, and it falls in the domain of prediction with domain of prediction with expert advice. I'll just explain what this is. So in a prediction with expert advice problem, there will be n experts and you want to forecast a value. Okay, n experts tell, okay, the value might be this. Okay, so you might accept the advice of one expert, and then you want to compare the reward you achieve compared to the rewards you achieve by choosing the best expert. Okay, in the hindsight. Okay, if you just choose one best expert throughout all n, for example, you are making n decisions throughout all small n, I mean the small n decisions. If your algorithm can give you which expert to choose and it learns from every iteration, then you want to try to minimize your cost compared to choosing a single best expert in every round. Okay, and for this setup, there are algorithms which achieves the regret bound root small n log capital N by 2. Just to remind you, small n is the number of rounds. Okay, you are doing this, and capital N is the number of experts, and the main algorithm is exponential weighted forecasting. That's one of the first algorithms that achieved this bound. And in our problem, the experts happen to be this thetas, right? The threshold at which you want to decide whether to offload or not. Okay, but this happens to be in the continuous domain. They are between 0 and 1. It's not a discrete problem as in the classical PEA. When there is continuous domain, the existing approaches use uniform discretization and they assume the total cost is convex or smooth. But in our case, in our problem, we don't have that facility. I'm just showing how the total cost L theta of y varies with theta for one small data set when beta equals 0.5. So we don't have convexity or smoothness. So for which we actually have to go with new algorithm and analysis. So then the first, I don't know. So Lee, how much time do I have?
I think it's 10 minutes.
10 minutes, right? Okay. Yeah. So I'll just give a very high level idea. So what we had is, even though the thresholds can take value between 0 and 1, once you know the p values for each of the images, all the thresholds that are within an interval formed by these p values, just focus on the figure below at the bottom. So if I have, say, so images arrived over n images arrived over time, so I look at the p values for each image and form these intervals. We have bn plus 1 intervals. So it happens that for our problem, within each interval, the total cost for all thetas within each interval, the total cost is same. Okay, so now we have non-uniform intervals, and then these non-uniform intervals forms our experts. Okay, there are small n plus 1 number of experts. So if I know all these intervals a priori, I can just use the classical exponential weighted forecaster to get to this regret bound root small n log n plus 1 by 2, where if you remember in the classical predictions with expert advice, in log n term, there is capital N, where n is the number of experts. So here that happens to be small n plus 1. And this regret bound is tight, okay? But then we don't know this p-values a priori. So that's one challenge. And how do we come across with across that challenge? Maybe I won't go to the details here. So what we do is we extend this exponential weighted average forecaster to the continuous experts case, and then we were able to come to the bound where we got this root n ln 1 by lambda mean by 2. So now, of course, we are paying a price here because we don't know the p-values a priori. If I know all the p-values, that means if I have all the n images at time 0 and I know all the p-values a priori, I said root small n log small n plus 1 by 2 is the best bound you can get. But I don't know that a priori, and the price I pay to that is by using 1 by lambda mean in place of small n plus 1, and lambda mean is the smallest non-zero difference between any of these p-values. Okay, that is the intervals bi, the minimum of the minimum length among all these n plus 1 intervals. So we are also able to show the computational complexity is O of t at time in round t. Okay, now I'll just give a comparison of how using HI helps using 4 different data sets and 4 baseline algorithms. We compare with Genie.
I'm sorry, Jaya.
Yeah.
Probably we need to finish this within 2 minutes, and then we will leave 3 minutes for the questions. Thank you. Okay, Lee. Yeah. So we have Genie, we have optimal fixed threshold policy, we have full offload. So DNN partitioning approach in our data sets and for this setup happens to be full offload approach. And no offload approach, that means we are just doing all the inference on the tinyML. And by the way, Genie is which exactly knows which images are wrongly classified and correctly classified by the mobile net. Okay, you can see here in this picture, the violet line here is no offload, and then that doesn't scale with beta because you're doing everything locally, right? And full offload scales linearly with beta. Now we see that the HILF, which is full feedback scenario here, is green, okay, and the optimal threshold theta star policy is in red. You can see that they both follow very closely, and the Genie is this straight line. So Genie actually scales linearly with beta, and it actually does better than both full offload and no offload scenarios. Also, HILF and theta star does better than no offload and full offload scenarios. And finally, the main point I want to drive here is given from this table. So Genie offload. So there are 3,925 images in this ImageNet data set. So the full offload is offloading all of them. Genie is only offloading the 2,230 images that were classified wrongly by MobileNet, and no offload is actually doing all the inference locally. So it is classifying all those 2,230 images. But you can say HILF and theta star actually gracefully does something in between. Okay, especially HILF, it actually sends less than 40% of the images it offloads, but then its accuracy after doing HILF is 77.4%, which is 20% increase of no offloading at all. Like, so if you're just doing on tinyML, you get 57%, but if you just use HILF, you can get 20% accuracy more. So that's the main gist of doing hierarchical inference, right? Sending less number of images, but still trying to increase higher accuracy. So with that, I want to stop here. Thanks a lot for your attention.
I'm happy to take in questions.
Thank you very much, Jaya. Thank you. And before any other more question, I saw that there is a question in the chat asked by Ali. So in the concept of measuring energy consumption, could you please tell us how we can measure network energy consumption?
Yeah, I mean, so in this work, we are not going into the implementation, right? So if you see in our future work, we want to test this idea in IoT environments, right? In that case, one needs to map the trade-off. So we mapped the trade-off here using a parameter beta, right? But if you're looking at the energy, you need to measure when you're transmitting, okay, how much energy consumption happens, and that depends on the wireless protocol, right? You use Bluetooth low energy or Wi-Fi or so on and so forth. So you need to measure that, and also measure till you get the inference back, right? Because there will be also some idle time which also consumes energy, like when the network interface card is up, right? So these measurements have to be, yeah, I mean, there are ways to do it. Like you either do measurement with respect to wall using an energy meter, or there might be some energy estimation techniques. So does that answer your question?
Sir, you said that the best that you can do is when the number of experts that you have is one more than the number of rounds. Is that correct? Like you had little n+1 as the number.
Right. So
yeah.
the best you can do, like, I mean, okay, say I'm looking at a horizon of n arrivals, right? Small n, right? If I know all these, for all these arrivals, all these images, okay, n images, I know a priori, if I know a priori what is that p-value, right? So for each image, you're sending it to MobileNet outputs the softmax values. Among them, the maximum value is the p, right? I'm calling it p. So if I know all these p values a priori, the best I can do is use exponential weighted forecasting algorithm and use the intervals as the experts, okay? And then I get root n log n plus 1/2. That is the best I'm saying, because it is the lower bound for the regret bound that any algorithm can achieve.
Okay, thank you.
Any other questions?
Last call. Any other questions? Okay. Okay. Yeah. I think we have a great presentation today, and we are perfect in timing. So let's thank again for Dr. Champati to share his insights in this work. Is that an ongoing work, or?
Yeah, I mean, actually it is. We are having a couple of works. I presented one of them. Yeah, it is ongoing vision. Yeah.
I see. Great. Thank you very much.
Thanks a lot, Lee. Thanks a lot again, everyone, for your time and hosting me, Lee. Thank you very much.
Yeah, our pleasure. Thank you.
Have a good weekend.
You too. Bye.
Bye.